Welcome to this session on step-up and step-down transformers. Today, we'll explore these crucial components of the X-ray circuit, essential for adjusting electrical conditions to produce X-rays effectively. Let's dive into how these transformers function within the system. In this course, you'll define a transformer and its role in transferring alternating current energy between circuits. We'll explore mutual induction, explaining how voltage is induced in the secondary winding. You'll identify key transformer components and their functions. We'll differentiate step-up and step-down transformers by turns, ratio, voltage, and current. You'll apply transformer equations to predict voltage and current behavior. Finally, we'll explain how transformers are applied in the X-ray circuit, focusing on kilovolt peak and filament control. The X-ray circuit is divided into two main parts: the high voltage circuit and the filament circuit. The high voltage circuit generates the necessary voltage to accelerate electrons across the tube for X-ray production. Meanwhile, the filament circuit provides low voltage, high amperage current to heat the X-ray tube filament, releasing electrons. On the primary side, connected to the main supply, key components include the line compensator for voltage stabilization, the auto transformer for kilovolt peak adjustment, and the exposure switch for controlling X-ray duration. Rectifier diodes convert alternating current to direct current, while the milliampere meter and focal spot selector manage current and focus size. Let's examine an X-ray circuit diagram. On the primary side, we start with the alternating current from the main power source at 220 volts. The line compensator stabilizes voltage, followed by the auto transformer, also known as the kilovolt peak selector, adjusts voltage levels that will be supplied to the step-up transformer. The exposure switch and timer start and control the X-ray duration. The secondary circuit begins with the second coil of the step-up transformer. The step-up transformer increases voltage. Rectifier diodes convert alternating current to direct current, and the milliampere meter monitors current during the exposure. In the filament circuit, the step-down transformer reduces voltage and increases current, heating the tube filament for thermionic emission. Now let's define a transformer. A transformer is an electrical device that transfers electrical energy from one circuit to another through electromagnetic induction. An important point is that transformers operate with alternating current, or AC. Why AC? Because transformer operation requires a changing magnetic field. Alternating current continually changes magnitude and direction, creating the changing magnetic flux necessary to induce voltage in another coil. A transformer can therefore change voltage without requiring a direct electrical connection between the primary and secondary windings. Transformers control voltage levels, allowing the operator to manipulate it safely. This is essential in X-ray circuits, where different voltage levels are needed for various components. Let's explore the structure of a transformer. It consists of three main parts: the primary winding, secondary winding, and a laminated magnetic iron core. Notice that the primary and secondary windings are separate coils. The primary winding is the input side of the transformer. This is where the incoming alternating voltage is applied. The secondary winding is the output side. Voltage is induced into this winding as a result of the changing magnetic field created by the primary. The windings are insulated and carefully wound around the core. This design ensures efficient energy transfer while minimizing losses. Mutual induction is a key principle in transformers. When alternating current flows through the primary coil, it creates a changing magnetic field in the core. This changing magnetic flux links to the secondary coil, inducing an electromotive force, or EMF. This process allows electrical energy to be transferred between circuits without direct electrical connections. The step-up transformer has more secondary turns than primary turns, which increases the output voltage. This high voltage is necessary to accelerate electrons for X-ray production. However, as the voltage increases, the output current decreases. This is exactly what we need in the high voltage portion of the X-ray circuit because X-ray production requires tens of thousands of volts across the tube. Let's explore the step-down transformer. In this component, the number of secondary turns is less than the primary turns. This configuration results in a decrease in output voltage while increasing the output current. The filament does not need thousands of volts. It needs relatively low voltage, but enough current to heat the tungsten filament to the temperature required for thermionic emission. Let's delve into the formulas governing transformers. Voltage is directly proportional to the number of turns in the windings, expressed as V2 over V1 equals N2 over N1, where V2 and V1 are the secondary and primary voltages. N2 represents the number of secondary turns, N1 represents the number of primary turns. So if the secondary has more turns than the primary, the secondary voltage will be greater. That gives us a step-up transformer. If the secondary has fewer turns, the secondary voltage will be lower. That gives us a step-down transformer. Conversely, current changes inversely with the turns ratio given by I1 over I2 equals N2 over N1. I1 and I2 are the primary and secondary currents. This means as the number of turns increases, voltage increases, but current decreases, and vice versa. For exam questions, first determine whether the number of secondary turns is greater than or less than the number of primary turns. Then predict the direction of voltage. Finally, remember that current changes in the opposite direction. Let's explore the differences between step-up and step-down transformers. A step-up transformer increases output voltage while decreasing output current, with more turns in the secondary coil than the primary number of turns in secondary coil greater than number of turns in primary coil. Conversely, a step-down transformer decreases output voltage and increases output current, having fewer turns in the secondary coil, number of turns in secondary coil less than number of turns in primary coil. Finally, let's apply everything we've learned directly to the X-ray imaging system. On the high voltage side, we have the step-up transformer. It operates by mutual induction with many more turns in the secondary winding than in the primary. Its job is to take a much lower incoming voltage and increase it dramatically into the range required for X-ray production, which is 40,000 to 150,000 volts or 40 to 150 kilovolts. This high potential difference is what accelerates electrons from the negatively charged cathode toward the positively charged anode. Before the voltage reaches the step-up transformer, the auto transformer and KVP selector establish the voltage supplied to the primary side. This ultimately determines the voltage produced on the secondary side and therefore contributes to the selected tube potential. After transformation, rectifiers convert the high voltage AC into pulsating DC before it is applied to the X-ray tube electrodes. Now look at the filament circuit. Here we use a step-down transformer. The secondary has far fewer turns than the primary, so the transformer reduces the voltage while increasing the current. The filament circuit provides approximately 3 to 12 volts and 3 to 6 amperes. That high current heats the tungsten filament sufficiently to produce a thermionic emission. The amount of thermionic emission ultimately affects the number of electrons available to cross the tube and therefore the tube current or milliamperes. So these transformers perform opposite electrical functions but work together toward one goal, X-ray production. That wraps up our discussion of X-ray circuitry and transformers. Remember, every component of the circuit has a specific role in creating the electrical conditions necessary for X-ray production. The key is not simply memorizing the components. Understand how electricity moves through the circuit and why each component is needed. Once you understand that relationship, X-ray circuitry becomes much easier to visualize and apply. Thanks for watching.